Welcome back to the organ printing course. So in this lecture, we'll discuss a very important bioprinting concept that has been developed recently in last few years. It is in situ bioprinting. Here, in situ means on the bed, on the patient. So this bioprinting deals with directly printing cells plus materials on the wound bed, patient's wound bed directly. So this process involves depositing, as you actually mentioned, as you already have discussed. Either you can use inkjet printing or extrusion bioprinting or laser assisted bioprinting to deposit cells plus matrix materials directly on the wound bed, patient's wound bed. So what we can do, we can use different other imaging modalities like laser scanning can be used to scan the wound bed, patient's wound bed, and then we can get to know, we can actually calculate the volume of that wound. And from there, suppose our interest is to print one particular tissue constituent like skin. So we know that skin is grossly in two layers like dermis and epidermis. So if we get to know the volume, we can determine how much amount of dermis and how much amount of epidermis is lost, and accordingly we can calculate, and then we can, that much volume of bioink can be deposited in a layer by layer manner on the patient would bed directly. So there, this process has several advantages. So let us see what is this process actually, and how, what are the different examples of this process, even the advantage of this process. Now, in situ bioprinting, as you have understood now, we have also seen that bioprinting has progressed rapidly over the past decade, right? And so that there are a lot of innovations, a lot of technological development. So that's why this in situ bioprinting has developed in the last few years as a process to directly deposit the cell-laden structure on the wound bed. So it has been, so that's why in situ bioprinting has benefited from different other innovations in biofabrication. And in situ bioprinting actually it allows the biomaterial to be printed directly into or onto the target tissue or organ. So that's the advantage. Here we are directly printing the construct on the patient's own bed. So in this case, there is no need to transfer or there is no need to pre-print the structure, tissue organ structure in the with the help of a bioprinter on a stage or thing, and then take it to the surgeons. To so suppose if you are interested to implant that, take it to the clinic, take it to the surgical room, the surgery room, and putting it on the patients or implanting it on the patients. So because in that process, when we actually pre-print the structures and then take it, so there is a transportation involved, pre-printing involved, transportation involved, and then put it that back onto the structure. So here that transfer of pre-made three-dimensional construct, that need is eliminated in this case. Okay, so that's why it is directly on the wound or defect area. And also another thing, suppose when we print, we are targeting patient's wound bed. There we need to employ cells, that is either patient's autologous primary cells or stem cells generating from the same patient, that we need to use, because otherwise there can be immune reaction and the immune rejection, associated rejection. So that's why in this case, mostly autologous stem cells or autologous primary cells are mostly used for bioprinting, and that is done directly on the patient wound bed. And there are many such cases or situations where in situ bioprinting actually favored over in vivo or in vitro bioprinting, where actually this thing is done. Suppose this bioprinting is done in advance and then it is being put into the patient. with this thing, because you see, most of the cases, like in or most of the cases, whenever there is an injury, the injury has a very uneven boundary, or the anatomical location is such that a pre-made construct cannot fit perfectly to that wound bed, because there can be a mismatch. Though with bioprinting we can print a customized tissue structure that can directly go into the patient's body and can fit directly with the patients. But there are many cases where the bioprinted constructs cannot actually fit into the patient's body, and there can be a misfit. And because of this, there are other challenges. The tissue regeneration process can get hampered if there is a not proper connection or attachment of that bioprinted construct to the wound bed. But when we are actually printing the tissue construct directly on the wound bed, here the deposited structure that can confine to this uneven geometry of that patient's wound bed. So here, perfect fitting of that bioprinted construct to the wound bed is possible in this case, and that's a major advantage because there is no gap between the bioprinted construct and the wound bed. So that definitely that helps in regeneration or better regeneration of tissue structures, or better tissue regeneration. So here, that confining to the and intended anatomical location of the living body, that is the most or major advantage of in situ bioprinting. But this technology requires a lot more improvement to fabricate complex tissue in situ, because here we are dealing with many technological challenges. Like, first thing is the requirement of cells. That many number of cells are required to bioprint, because you know that in anatomical location any of the tissue, suppose skin, the cell number present in a suppose in a 1 centimeter by 1 centimeter square is skin, the cell number is present is huge. So if we are trying to achieve that in vivo cellular concentration or cell density, then we have to use huge number of cells, and also that depends upon the affected area. If the area is large, the cell requirement cell number is large. So that is one challenge. So that cell culture, different cell culture technology, how we can grow that many cells, even cell isolation, how we can isolate cells, or even different other things, how we can actually generate that particular type of cells by either by starting maybe, if we are targeting iPSCs, then getting one type of primary cells, then differentiating towards iPSC, and then again differentiating towards the target tissue, target cell type. So these things, these technologies has to be matured, and this technology has to be incorporated within our bioprinting. Other thing is that bioprinting technology has to be such that it should not induce any type of toxicity or any hazardous condition. It should not induce to the patient's body, because here we are directly printing on the patient's, and patient's wound is highly delicate. So then there should not be any temperature change, pH change, even any other all other physical properties, chemical properties, these all things has to be related. So there also these things also are very much required. Then the resolution of the printed structure, because here we are dealing with a very complex shape, so the resolution can be very required to be very good to actually confine to that, but that complex geometry. The other thing is, the most of the bioprinter, they able to print mostly on a 2D plane surface. But when the surface is suppose the undulating surface or wavy surface, so how the bioprinter now it would help, how the bioprinter would be able to print the structure in that undulating surface or in that wavy surface, or in that surface where it is a non-planar surface. So that kind of technological capabilities should be there. And then the other thing is, what kind of materials to be used, whether that material is if we put that material directly in the body, would it cause any toxicity, would it cause any reaction? So this kind of things also needs to be understand and deals with that. So that's why a multidisciplinary approach is very much required for in situ bioprinting, and bioprinting also multidisciplinary approach is required, but for in situ bioprinting it is very true to have a multidisciplinary approach and have a multidisciplinary innovation with tissue engineering, so that we can tackle this. We can actually come up with better strategies for in situ bioprinting. Now let us discuss the advantages. Already we have discussed certain advantages, like as I have mentioned earlier, the main advantage of in situ bioprinting is the need or is the need, no need of transportation or pre-fabrication of the structure. But if you see in the ex situ tissue engineering bioprinting, where it is the bioprinting is done mostly in the lab, and then the tissue construct is taken to the surgery room. So their transportation, prefabrication, all these things are the major challenges, major things to be tackled from the printer for application of tissue organ. There, it increases the risk of introducing an infection to the material that can be passed on to the host. So during that transportation or even for culturing, that time suppose infection some infection gets introduced, so that can be passed to the host. So we need to be very cautious about this thing. But when we actually deal with in situ bioprinting, there, because this process transfers the biomaterial to the patient wound bed directly, so that's why this process eliminates the many of these associated issues of ex vivo bioprinting, like this fabrication is here is the fabrication is directly on the wound bed, so there is no requirement of prefabrication time, and also the the process becomes one step where directly we can print on the wound bed. So it eliminates that earlier process like fabrication, then culturing, storing, then transporting. All these things can be easily get eliminated if we use in situ bioprinting. So this is definitely, this has the advantages over the ex situ bioprinting. In situ bioprinted constructs may also demonstrate improved functionality and integration compared to ex situ printed implants due to benefits incurred from the natural cellular microenvironment of the body. This is another thing. Now, when we directly print a structure on the body, so the that body cellular microenvironment that is providing as a bioreactor kind of stuff, like say that. So what, so that is providing all the necessary condition to the bioprinted constructs, right? Like the all type of signaling mechanism can be now can be possible, where we print the structure on the directly print that on the wound bed. So that's why, but in ex situ, in the initial stage, unless we implant the structure, those things are absent. We have to culture in a different conditions. So those things, so that's why that is also one major advantage of in situ bioprinting, because here we are directly using the patient's wound bed as a, and that is the host, and there it can now the process is that tissue regeneration will be much faster, because the thing is that there is a proper attachment, there's a there's a proper, suppose there is a proper functioning of the structure, and then there is all these other associated challenges or other associated benefits. So that's why in situ bioprinting has several advantages, and now there are some studies where they have tried to use this in situ bioprinting concept for better tissue regeneration. Actually, there are some studies where they have shown the possibility of using in situ bioprinting concept for better tissue regeneration application. Now, in this lecture, we'll discuss a few literatures or few studies where they have shown the possibility of using in situ bioprinting. So we'll take some examples, but please go through all the, I have listed a number of references with the along the, in the slide, within the slide. Please go through this for further reading and for further understanding. Like this is mostly, I have taken this from this reference. You can look into this, the reference. There they have discussed the what are the current bioprinting techniques, that is that with that actually the in situ bioprinting is possible, and also what are the other ways, like there are some some projected thing, like where what are the other different bioprinting techniques can be used for in situ bioprinting. Like one such thing is the traditional in situ bioprinting move along the XYZ axis while depositing bioinks on the chest, suppose on the chest wound, according to a computer model. Suppose there is a in the chest, suppose there is a wound. With conventional bioprinter, we know that conventional bioprinter that moves in XYZ direction, and by this way that can deposit the structure directly on the wound bed. So in this kind of conventional bioprinter can be used when the wound is present on the surface of the body, like skin, that is easily accessible. That kind of structure, suppose that part is easily accessible by some with the bioprint with this bioprinter. So that in for that kind of applications, conventional bioprinter can be very well be applied. So that suppose this patient is like the patient is lying on the surgical bed, and then a computer edit and the bioprinter is also stationed within that surgery room, and then it is being the bioprinting is done. So this kind of concept, this kind of thing is a very powerful technique to tackle the many associated challenges as I have mentioned earlier, and also it helps to heal the wound much faster. The next this thing is the suppose to for bioprinting in some anatomical location where it cannot be accessed from the outside, without opening the without opening that wound. So this thing, suppose that is not possible, so that can be for doing that kind of things, robotic arm assisted bioprinters can be very healthy. Suppose here they have shown the examples of, suppose here they have shown the examples of this robotic arm dispensing, where suppose there is a cartilage defect in the cartilage tissue. Cartilage is basically present in our joints. It is the cushioning surface between the joints which is attached to the bone. So thus suppose there is a defect in the cartilage, and then this robotic arm assisted bioprinting can deliver the cartilage tissue specific bioink within that defect. Now here this has definitely this has advantages because of the it this robotic arm can actually positioning the bioink. It can actually penetrate that within a small surgical small, if a small cut can be made within that, the printhead can go into that location, and it can have print, it can print the structure within this, because this robotic has a high degree of freedom. Because of that rotational freedom, it can deposit the bioink within this kind of conditions when there is a challenging to print the directly thing. Similarly, magnetic nozzles are another thing, where suppose we need to print something beneath the skin, a structure needs to be printed. Then what happens, this magnetic needle can be used for printing the structure beneath the skin surface through magnetic actuation, because here the magnetic actuation can be possible, but that can leads to printing this kind of structure beneath the skin. So whenever, like, suppose a something has to be printed below certain structure, like in this case skin, so that kind of parameter thing. Other than this, semi-automated semi-automated bioprinting techniques can also be employed, like this thing. Photo cross-linking light that is assisted or light sensitive biopolymers can have been injected into the dermis by intervertebral 3D bioprinting, intravital 3D bioprinting, and then a light can be passed to this defect for bioprinting of these structures. So this kind of things are very powerful. So this injection, first this hydrogel is injected within the defect area. Then the next part is done. The light is exposed to cross-link that hydrogel. So this kind of thing is very important. For suppose there is a defect within the some structure, somewhere inside the thing, maybe inside skin or somewhere inside the body. Now what happened, with a injection we can inject the bioink in that defect, right? And then through that small hole we can put a a light source or a light can be passed to that thing, that area where the hydrogel can get cross-linked by light exposure. Right? So we can choose a wavelength that is not causing any toxicity or not causing any reaction with the body. So that kind of things can be very well chosen, and then this kind of bioprinting can be very well possible. The other thing is ionically activated. In ionically activated, what we can do, we can print a sheet of biomaterial onto the, suppose onto the dorsal full thickness wound by delivering hydrogen precursor solution and cross-linker solution concurrently to wound site using a handheld bioprinter. This is ionically activated. So here we can have this kind of handheld device can be developed. So we'll discuss one of such things in the next coming slides, where how we can have a handheld bioprinting device. So then this can be ionically controlled, and it can actually print the, suppose the some biomaterials plus cells onto the wound bed directly, and then can be cross-linked by either by photo cross-linking or other ways. Similarly, this light activated by this handheld bioprinting, where what happened, it is here also a photopolymerizable bioink can be injected. Suppose there is a muscle injury here, it is showing the muscle injury. So within the muscle injury, suppose a photopolymerizable bioink injected there, and then also through this device, this suppose this device also has another attachment for projecting light to this particular area, then the bioink can be cross-linked. So these are two are some examples of how a handheld device can be very well be employed for bioprinting this kind of structures. So these are some examples where bioprint how different types of bioprinting technologies can be employed for printing better, for printing some structures of parties of different anatomical locations. Suppose whenever it is on the surface where it can be easily accessible, there some conventional bioprinter can be used. Robotic arm can be used wherever there is a high degree of movement or freedom is or rotation is required for the bioprinting. Suppose the bioprinting nozzle or the print head, that their robotic arm can be used. Magnetic nozzle can be used without, suppose without touching the thing, the by magnetic actuation the printing can be possible. Semi-automated, where suppose intravital 3D printing, where we can inject the bioink within that defect area, then that can be cross-linked by photo light exposure. And in case of handheld, either it can be ionically activated or light activated bioprinting are possible. Let us now discuss about the different bioinks that has been used for in situ bioprinting. So please remember, these bioinks are already being used for conventional bioprinting, where these have been or these bioinks have been used for different applications, and also different types of gelation mechanisms or strategies have been used. Or also in this case, in this particular literature, they have projected. So these bioinks can be used, definitely be used for in situ bioprinting for a particular type of applications. Like the very first thing that is here given here is the enzyme activated. Like suppose, as we have discussed, enzyme based cross linking mechanism is one most prominent prominent strategy for certain types of bioink to use them for bioprinting of different types of structures. And also either this can be this type of bioinks can be used by extrusion based or inkjet based or even laser assisted bioprinting, where we need to just consider that what is the material, what is your substrate, and what is the enzyme that actually that initiates this cross-linking mechanism. Like here, they have given example of. Let me switch on the. Yes. So here they have given example of this enzyme-activated bioprinting when like fibrin plus thrombin, and we know this very well. Suppose when fibrinogen comes in contact with thrombin, then that reaction, the thrombin acts as a cross-linker and that fibrinogen will become fibrin gel, right? And it will become a crosslink gel. So this strategy can be very well used, and actually this strategy has been has been used for various applications. Whenever there is a, suppose like in case of cornea, such this glue, this surgical glue is nothing but this kind of this fibrinogen plus thrombin, where these are two comes in two components, where if you when you mix these two, fibrinogen plus thrombin, then the cross linking can be started. So this type of, so the suppose we use, so two different bioinks can be used here, like one is the fibrin bioink, where fibrinogen bioink, where MSCs or any type of cells can be loaded, and that can be first printed, and on top of that, if we print the thrombin crosslinker, then the whole construct will get crosslinked. So this example is a very good example how enzyme activated process like this kind of can be bioinks can be used for bioprinting applications. So and this in this case the cross linking is instant, so it will become just a within few seconds this whole thing will become cross linked, and there become other important thing is also this, when the fibrinogen plus MSC is when we put that into that wound bed, as you can see here, it can confine to that volume or to that area of the wound, perfectly filling the defect volume, and then when we put thrombin, the whole thing will get cross-linked, and so this can be very well used for this kind of this when for in situ bioprinting applications. The next thing is the pore forming bioing, where suppose we use something like Gelma plus PEO as a bioink, and where it suppose loads one type of cells, suppose for it is skin, so fibroblast maybe. And then we know this, we have already discussed this, Gelma is a photosensitive material. So whenever we if we and we also add some photoinitiator, and whenever we switch on light, the photoinitiator will get activated and the Gelma will get cross-linked because of the presence of this methacrylate group. So it's a photosensitive material. Now suppose with the bioprinting nozzle, we deliver Gelma plus PO plus Bioink and plus fibroblast. And then the light is on. See, suppose in this case, so it's UV light. Based upon the photoinitiator, we can use different types of light, different wavelengths. But I suppose if we use a photoinitiator can get that can get activated at this like UV light, that wavelength, typically that wavelength, then so it will become a gel. Then PO is a material, so that is a water that can be dissolved away. So what will form? It can form a pore forming. Suppose when the gelma plus PO, this thing is put it here with the cells, then UV light is on, whole thing get cross linked, so whole thing is getting solidified and is become a gel. Now from there PO, when the PO is out, now PO leaches out, then what will happen? Then we get a porous for pore forming structure. So this technology can be very well used whenever we are trying to develop, like whenever we are trying to bioprint a construct with a porous with some porosity, and porosity helps for different applications, like it can be for cell migration, cell even for nutrient transport, and also these pores can be available also for the suppose the new tissue growth here, the tissue in growth happens from the surrounding native tissue, that times these pores can become handy. The next thing is another example or another strategy could be where suppose we incorporated some kind of oxygen generating particles, or in this case they have used microalgae. So this algae is actually, this microalgae actually can been can be incorporated with gelma plus alginate bioink, right? This bioink combination, gelma we have already discussed, gelma is a photo cross linkable bioink material, and alginate is a natural biomaterial, right? Now whenever this bioink, suppose then the microalgae is incorporated within this, and then that can be printed. Now the microalgae generates O2. Now this kind of O2 generation can help for chronic type of wound healing. So whenever there is a chronic wound healing to treat chronic wounds, this strategy can be very well be employed. So this is to in situ bio with oxygen generating material. The next thing can be, suppose we are interested to deliver particular type of growth factor. So then what will happen? Then that can induce different types of tissue engineering. Suppose when you are it suppose it is used for maybe for blood vessel generation. So BEGF can be incorporated for bone. Again, BMP can be incorporated for suppose for cartilage TGF beta, or suppose like this different types of growth factors, targeted growth factors can be incorporated within this bioink, and then it can be cross-linked further with by using employing different types of mechanisms. Like in this case they have used Gelma, so it can be crossed by photo light, right? So then what will happen, this can be put into that particular defect area, and then based on like this in this case where the light on, by switching on the light, this can be solidified, and this can be used as a template for this growth factor delivery. So this growth factor eluting bioink can be very well used for different tissue regeneration. Like in this case, suppose this case they have shown the possibility of for muscle tissue. So for muscle tissue, specific type of bioink can be incorporated, and that can be employed here, and that can lead to suppose more muscle, better functional muscle recovery. So this is one such example where this particular type of growth factor eluting bioink can be employed for this thing. The next thing is conductive bioink. Like in this case, hyaluronic acid and polonic F127 incorporated, and these two are used as a bioink, and then that is being used for bioprinting of them. In this case they have printed in the liver. So this kind of conductive polymer helps in better tissue regeneration. This can be employed for different other types, like for cardiac tissue, for nerve tissue also. Conducting polymers can be used, and that can conducting polymers can be incorporated within with different types of other materials, and then can be employed. That can be used as a bioink for bioprinting in that particular area where we where this helps for better tissue regeneration. Right? So these are the some of the application of bioinks, but different other types of bioinks can be used, like alginate has been given one. So alginate can be also can be used like in that way, in that fashion. Like suppose if we put alginate construct or alginate lines, and then a spraying mechanism with calcium chloride can be employed when this after printing the first layer, say a calcium chloride spray can be employed, and that spray this calcium chloride, that particles generated microdroplets, that can actually cross-link the alginate structure. So this is another strategy by which this is ionically cross-linked. We have already discussed this ionically cross-linked material like this alginate can be very well employed. Similarly, collagen can be also employed for this kind of in situ bioprinting, because collagen, we know that most of our tissue, it has a collagen as ECM components. So we can employ or we can use collagen to print the structure. And collagen, another important thing is this: collagen is a thermosensitive material, because when the collagen is solubilized, it is solubilized in acidic solution. After that acidic solution, the because we cannot use that low pH for any tissue, any for this kind of in situ bioprinting. So we need to adjust the pH. We can adjust the pH by maintaining the temperature below 15 degrees centigrade. That time collagen will not become again solubilized, again insoluble. That means collagen will not get solidified. But if that pH adjusted solution, if we can increase the temperature to 37 degree, it will become cross-linked. Or the self-assembly of the collagen will happen, and it will become cross-linked. And by this way, we can form different types of. So by this way also we can use this collagen for in situ bioprinting by putting the collagen in that wound bed, and then because the wound bed in our body, the wound bed has typically the temperature of around 37 degrees centigrade. So that will provide as a the temperature that induce the cross linking of this collagen molecule, and it will become gel. So collagen also can be definitely used for in situ bioprinting. Similarly, there are different other materials like decellularized extracellular matrix. We have discussed this before. Decellularized extracellular matrix is like when we decellularize the tissue and to throw out all the cells and then use that acellular matrix for bioprinting matrix acellular matrix for hydrogel preparation, and that hydrogel can be used for bioprinting because decellularized extracellular matrix, the major component of this is the collagen. It's a collagen based, and there are other proteins and carbohydrates, bioactive factors. All these things are there in decellularized extracellular matrix. So what we can do, we can use similar concept like how we discussed about this collagen printing. Similarly, we can print the structure with decellularized extracellular matrix pressed by Bioink, and then that also becomes a thermosensitive material, so it will also become gel at 37 degrees centigrade. So when you print that DCM structure on the wound bed directly, if we then within few within some time, it will become gel and it will get cross-linked and it will integrate within the body structure. So digital extracellular matrix can be another candidate for in situ bioprinting. Similarly, there are various other types of materials, and I will encourage you to look for more and more examples, and in the literature you can find several examples where people have used different types of materials. Similarly, some groups have used gilma plus hyaluronic acid methacrylate. Now gilma plus HAMA, hyaluronic acid methacrylate, so these two combination also is also a photosensitive or photocross-linkable materials, and we will discuss in the later slides how some people have used this concept. Similarly, for inkjet-based bioprinting, we can use different low viscous polymer solutions, even cells for bioprinting within direct wound bed. Suppose we uh, suspend the cells in some buffer and then directly those that can be inkjet bioprinted. Like inkjet, we know that inkjet bioprinting, the main principle is generating droplets, and that mostly water-like viscous material. That's why we can suspend the cells in that buffer or media, cellulose media, and then that can be directly printed on the wound bed. So the cells can be positioned directly on the wound bed, on typically on that particular area. So this can be used. Inkjet bioprinting can also be used for this purpose. Again, laser assisted bioprinting can also be employed, and there also we can use different types of Bioinks, and we know that when the laser light is on, it is generating the droplets are getting generated again from the ribbon, and that is getting deposited on the substrate. Now that process directly on the wound bed using the laser assisted bioprinting, we can deposit the cell laden hydrogel on the wound bed using this thing. And there are various types of materials. In one such application, people have used hydroxyapatite slurry, where and then hydroxyapatite slurry directly has been printed on the on the wound bed, that is on the bony wound bed, that is the calvaria bone on the animal. Of course, they have printed this thing. So different strategies can be employed, and different types of bioinks can be used for this in situ bioprinting. And please look for more and more examples in the literature. I will also discuss a few more examples in this lecture.